4.3 Inverse functions. So far we've been talking a lot about functions. We've been talking about what is a function, how do I evaluate a function at a point, and more recently, how do we do operations on a function. In particular, we talked about this thing called function composition. So we're going to mention up our composition in this section again, but before we do that, let's go ahead and talk about this particular type of function. So our first definition for today. If I have the graph of a function f, and if every horizontal line intersects my graph at most once, then we say f is a one-to-one function. This is very similar to what we did before for regular functions. Remember, for a regular function, we had the vertical line test. Well, for here, we have something similar called the horizontal line test. The vertical line test told us if we were a function, whereas the horizontal line test tells me if I'm a one-to-one function. So, looking at example 1, determine if the following are one-to-one functions. So, for the one graph on the left, I want you to imagine that we have a flat horizontal line that's moving from top to bottom. As I move my line from top to bottom, is it true that this horizontal line only touches my graph at one point each time? Well, if you look at example 1, I can draw a bunch of horizontal lines to indicate how I'm moving it down. All of my horizontal lines only touch my graph at most at one point. So in this case, I would say yes, I am a one-to-one function. What about the second one? You might be tempted to say, all right, if I draw a horizontal line up here, then I touch my graph once. But we gotta be careful, we're checking every single horizontal line. If I look at this horizontal line here, I can see that this horizontal line touches my graph twice. Well, if it touches it more than once, then no, we are not a one-to-one function. So we have our horizontal line test. So why did I mention a one-to-one function? What was the point of that? And how does this tie in with my function composition? So now we can finally define the inverse function. If I have a one-to-one function, then I can find the inverse function. Here we denote it with an f to the -1. It looks like a power, but it's actually a superscript. This inverse function undoes or reverses the work of my original function. In particular, we have this one very nice property of the inverse function. If I have a one-to-one function, f, and an inverse function, f inverse, then they satisfy the property where if I do their composition, remember compositions whenever I plug one function into the other, I get exactly x, regardless of the order of composition. So we're going to focus on this property. For example 2, I want you to say, if I have the function f of x, 3x plus 4, and g of x is 1/3 times x minus 4, can you tell me if these are inverses of each other or not? Well, I know that two functions are inverses of each other if and only if, whenever I do their composition, I get x. So let's go ahead and do f of g of x. If these are inverses, I should end up with a plain x. So if I translate this over, I can write this as f of g of x. Well, I know what g of x is. Here I know g of x is 1/3 x minus 4. So now I'm asking, if I plug this entire expression, actually let me go ahead and rewrite this in a different color. Let me use red again. 1/3 x minus 4. That is, if I take this entire expression and plug it into my function f, do I get x? As a reminder, we always have this helpful notation where if I want f of x, I can always imagine it as f of a blank. In this case is equal to 3 times that blank plus 4. So in this case, I want f of 1/3 x minus 4. 1/3 x minus 4. So that means this is equal to 3 times 1/3 x minus 4, being very careful with my parentheses, plus 4. So let's see what happens here. Well, I have 3 times 1/3. 3 times 1/3, they cancel each other out, or you can say 3 divided by 3, I get 1. So I am left with x minus 4 plus 4. Well, minus 4 and plus 4, I get x. So this follows my first property. If I do their function composition, I get x. You can also check what happens if I did g of f of x. You'll actually see that I also get x by itself. So this means that yes, f and g are inverses of each other. So again, if I do their composition and they are inverses of each other, I should have an x. If I had any other answer besides an x, I would say no, these are not inverses of each other. So for example 3, take a minute to see if you can do something very similar. I'm asking the same question, but with different functions. See if these two functions, f and g, are inverses of each other or not. I would recommend pausing this video for a moment. What I'm going to do is, after a few seconds, the solution will pop up on this video. And if you got it correct, that's great. If you did not get it correct, you can go ahead and pause the video to see what work you were missing. All right, so for the answer, your final answer should be no, because whenever you do this function composition, you actually end up with x minus 16 instead of a plain x. So again, if you did get the answer no, perfect. If you didn't, take a moment to pause the screen and see where did you accidentally make a mistake. Well, for examples 2 and 3, these were great if I gave you two functions. If I gave you two functions, you can tell me instantly if they are inverses or not. Well, I guess not necessarily instantly, but through some work, you can tell me. Now, what if instead I gave you one function and I told you to give me the inverse? So that's what we're going to be doing next. So what I have here is an outline of how do we find the inverse of a function if you have one given function. If I want the inverse, f inverse, the first step is I change my f of x into a y. Then I swap my x and y in my equation. I then solve for y and change my y into f inverse of x. So it's better if we go ahead and go straight into our example and see what's happening here. In example 4, determine the inverse of the following functions. For part A, I have f of x is equal to 6x minus 1. So if I follow my steps, I'm going to go ahead and change my f of x into a y. That's step 1. Let me go ahead and write a 1 here. Step 2, I go ahead and swap my x's and y's. That means anywhere there's an x, I make it into a y, and anywhere there was a y, I turn it into an x. In this case, I have x is equal to 6y minus 1. Notice here that I changed my color because I want to indicate that this is no longer the same equation. I have a new equation. Now, continuing through step 3. Step 3 tells me solve for y. So this is where I start for step 3. If I want to solve for y, I would go ahead and add 1 to the left and right, giving me x plus 1 is equal to 6y. And then I can divide by 6, giving me, let me bring it up here, y is equal to x plus 1 all over 6. So I solve for y. That's my step 3. And then my last and final step is once I solve for y in my new equation, I turn it back into an f, or in this case an f inverse. So using this, I can find my inverse function. Meaning if I compose 6x minus 1 with x plus 1 over 6, I should get x. So now that we're done with part A, let's go ahead and look at parts B and C. For B, I have f of x is equal to x cubed minus 2. And I'm going to follow the same steps I did before. For part B, we have f of x is equal to x cubed minus 2. If I follow my previous steps, I start by changing my f of x into a y. And then I swap my x's and y's. Now I must solve for y. To solve for y, I can do this by adding 2. giving me x plus 2 is equal to y cubed. And then taking the cube root. If I take the cube root of the left and right, so I gotta fit it in here, I should be left with y is equal to the cube root of x plus 2. I solved for y, and all that's left for me is to replace my y with an f inverse of x. So the inverse in this case, I should get the cube root of x plus 2. Thus, I'm finished with part B. Last question for this video. Same instructions, find the inverse for g of x is equal to 5 over x plus 2. If I simply follow the same steps, replace my function with y, and then swap my x's and y's, I get x is equal to 5 over y plus 2. This one I do have to do a little bit more work. Here, mainly because my y is in my denominator. If I want to clean this up, that is, I want to solve for y, I must multiply by y plus 2. And there are several ways you might be writing this in the product. The way that I'm going to write this is, allow me to write y plus 2 times x is equal to 5. Notice I did not multiply my x and my y plus 2. One way I might encounter this is, what if I just divide the left and right by x? If I do that, I'm left with y plus 2 is 5 over x. And then all I have to do to finish up my problem is subtract 2 from the left and the right. I'm going to go ahead and move this upwards for space, leaving me with y is 5 over x minus 2. Or in other words, g inverse of x is equal to 5 over x minus 2. Notice this time I said g inverse instead of f inverse. That's because my original function was a g, so I should maintain the same lettering. In any case, I have my final answer. And so that finishes up our video for